So, well, the previous section, the section 4.1, talked exclusively about uh, quadratic functions. We went through all the properties and the elements, the essential elements that is needed and the parameters that can be used for a quadratic function. The section 4.2 will extend the conversation over all polynomial functions. All polynomial functions. Again, a polynomial function in general form of degree n can be written as f of x equals, if I call a1, a sub 1, the coefficient of x power n. So that means let me call it a sub n. That's the number that is the coefficient of the leading power of the variable, which will be called the leading term. That's the leading term because that's the term that will be seen as the term with the highest exponent. And then we can have another term, but I'm going to call this one another because we're just naming it a sub n minus 1 for x exponent n minus 1, which will be the next term, the next power. N minus 1 will be the next power after the highest one. And then so on, we can continue having terms until we have the last term, a sub 0, which would be the constant. An example can be if you have n. Let me give you a quick example. If n, a polynomial of power n equals 4, can be written as, because remember the quadratic functions are also polynomial functions. The degree is 2. But in this section, we will extend the conversation over every polynomial functions. So now if I take an example of polynomial function degree 4, that can be seen as f of x equals 2x to the power 4 minus x to the power 3 plus 7x exponent 2 plus 3x and then minus 5. So that's a polynomial. And then your leading term is 2x squared. That's your leading term. And then the leading coefficient will be the 2 with the number with the variable that support the highest exponent. So that is a polynomial of degree 4 because the n now, which is the exponent of the highest exponent of the variable, which will be n, and n equals 4 in this case. So that is a polynomial function. And you see, in this case, we will be talking about the zeros. The first thing we're going to talk about here is the zeros or roots of a polynomial function. The zeros or roots of a polynomial function, zeros or roots, are the values of the variable that make the polynomial equal 0. So x values for which for which f, the polynomial function f of x is equal to 0. So if you plug in an x value and the result come out to be 0, then this value is called a 0 of that polynomial function. Now, we can talk about the multiplicity of the 0. The multiplicity of the 0 is if you have a certain power of this factor. So if you have x equals 0, if you have a function, a factor x minus r that is equals 0, then x equals r will be a 0. But if you have a certain power of it, let's say p equals 0, that means that that factor itself is 0. It has it is present in the in this expression p times, and that represents its multiplicity. R equals 0 is the 0. I mean, x equals r. R represents the 0, and the number of times this factor repeats in this expression represents the multiplicity of this 0 or root in this polynomial. Say, for example, you have a polynomial f of x that equals x minus 5 to the third power times x plus 2 squared. Well, if you expand this expression, it will give you a polynomial of the highest degree through 3 plus 2. 3 plus 2, which will be 5. Because this factor repeats in this expression 3 times, and this one repeats in this expression 2 times. And when you expand, this will give you a polynomial of degree 3. And expanding this will give you a polynomial of degree 2. And then you would multiply them again, and the highest degree would be 5. But what we are talking about here, we are trying to see, to make it clear what is the zeros, and then what we call the multiplicity of each zero, and the effect of the multiplicities, the effect of each multiplicity on the graph of the polynomial. Now, we need to remember that if you have, let's describe this here. When we have a 0 that is a 0, if R is a 0 of even multiplicity like this one, then the graph of the function, what is the effect? We have two different effects. We have A, the graph crosses the x-axis at this value. And B, the graph touches the x-axis and turns. Those are the two effects we can see happening on the location of each zero. Well, we need to remember, when you have x equals r, that means this is a value at which the graph crosses or touches the x-axis. But if the multiplicity is even, you're gonna have a certain effect. And when the multiplicity is odd, you have a different effect on the graph. Now, even multiplicity is what we want to talk about first, is when the graph touches and turns around. So if x equals 5, for example, let's look at the other one instead. If x equals -2, because that x equals -2 would make this part equal 0, with this exponent 2, with this exponent 2 for the factor x minus x plus 2, x plus 2 would give you a 0 that is x equals -2. But because there was an exponent 2 for the factor, it gives it a multiplicity. Multiplicity was 2. Multiplicity is 2 because this factor x plus 2 repeats in the expression 2 times, which is even. Then on the graph, what you're going to see at x equals -2 is that the graph would bounce. It touches the x-axis and then turns around. And then another situation. I mean, remember I told you that it was 2 situations, right? One, you can cross the x-axis, and one, you can touch the x-axis and bounce. The one you touch the x-axis and bounce is when the multiplicity is even. You touch the x-axis and bounce. When the multiplicity is odd, then you get the other scenario. So if R is 0 of odd multiplicity, the graph of the function crosses the x-axis. Crosses the x-axis. So the expectation is something like we are looking here. I give you this example so we can talk about this situation that we just described. I have this graph here. I have multiple, and I marked the location of the when the graph crosses or touches any moment of the trajectory of the graph that the graph meets with the x-axis. I point them out on this curve. They happen at x equals -6, x equals 0, and x equals 4. So all these values, or we can call them zeros, of this polynomial that was graphed here, the zeros or roots of the polynomial f of x graphed are -6, 0, and 4. Now we can tell what happens in each situation. X equals -6, what happened is we can see that the curve slowly crossed the x-axis, but it crossed it. Now we will talk later about when the cross is slower and when the cross is quicker. Well, quickly we can say that the higher is the odd multiplicity, or in general, the higher is the multiplicity, the slower would be the effect on the x-axis. Let me explain that. Say if I have x minus 5 exponent 5, we have a multiplicity 5, which we know the graph at x equals this value that makes this inside expression equal 0, which is 5. At x equals 5, we expect the graph to cross the x-axis because the multiplicity 5 is odd. But it will not be as quick as if you have x minus 5 exponent 3 or x minus 5, just that. See, the powers 5 is slower, will be slower than 3, and the quickest will be when the power is 1. So here I would say this is 1, it's quick, and this one is slower. And this is not the conversation we're having. I'm not gonna say what is it now, but later on we will see how far in this class, we would anticipate looking at the graph. But we have to see that whether it's even and odd first. We want to see whether it's an even or odd zero, multiplicity. So at x equals -6, x equals -6 is a zero of an odd multiplicity. And I said that multiplicity equals 3 because clearly the difference of the cross is slower here than this one. At x equals 0, what do you see? What is the effect of the x on the x-axis? Well, clearly you see that it didn't go through it, right? It touches the x-axis and bounces. That's when you know that you have an even multiplicity. And I say that in this case, it's 2 because 2 would be the quickest bounce you can anticipate. So a bounce like this, when it sits before returning, we see how slow this would be, then it would be a higher multiplicity. And then at x equals 4, we also have a cross, but the multiplicity is 1 because you see that it crosses quicker. Quicker than at x equals -6. So the quicker it crosses, the lower is the multiplicity. The quicker the graph crosses the x-axis, the lower is the multiplicity, odd multiplicity. The quicker the graph crosses the x-axis, the lower is the multiplicity of the odd multiplicity. The quicker the graph bounces on the x-axis, the lower is the even multiplicity. So our next example here, it says, given the graph of the polynomial function below, complete the table of values for either the x value of the 0, that means where the graph crosses the x-axis, or the multiplicity of the 0. Now let's go ahead and look at the graph of the function here. Now, first thing we want to do, since the conversation is about zeros, then we're looking for where the graph crosses the x-axis and the effect or how. So it's about where the graph, when the conversation about zero, if you are looking for zeros or roots, you're looking for location where the graph crosses the x-axis. So that is when you're looking for zeros. And when you're looking for multiplicities, the question now is about how the graph how is the contact, how the graph react when being in contact with the x-axis, or when reaching the x-axis. Let me put that. So the how, whether it crosses it or touches it and turn. So roots, location, and multiplicity, how? Cross or touch and turn. So um now we have this, and this. So we have 3 zeros, but we know because they said earlier that this is a polynomial of degree 4, this is quick cross, that's multiplicity 1, -1, -5 is a quick cross, it's a multiplicity 1, -1 also multiplicity 1. Well, we have only 2 because the sum of the multiplicities will give you the degree of the polynomial. So this one, it bounces and it touches and bounces, so that makes it a multiplicity even. But since the multiplicity, the degree of the polynomial, we said it earlier, was 4, we already have 2, so even makes this one 2. So now we know that we have -5, but also we have -1 to be multiplicity 1. And the only multiplicity 2 we have, it's x equals 5. X equals 5. And I explained a little bit here. The graph crosses the x-axis quickly at x equals -5 and -1. That makes the zeros, these zeros, -1 and -5, with a multiplicity 1, and the other 0 where the graph touches the x-axis is a touch and turn around, and it's quick also. as quickly as we can imagine, then x equals 5 would be a multiplicity 2. And when you combine all the multiplicities, 2 plus 1 twice, that would give you a total 4, which is the degree of the polynomial. So next example here, they want us to consider this function, this polynomial function, this time in the equation format, versus earlier we had the graph of it, but now we have the equation in factored form. So when it's in factored form, how do you identify the zeros and their multiplicities? Because the question they're gonna ask me here is to determine the x-intercepts of h, that means where it touches the x-axis, and the multiplicity based on the equation. Remember, we were looking at the graph and see the impact on the x-axis to determine whether we have an even or odd zero, and to determine whether we have an even or odd multiplicity and the value of the zeros, the where and the how. But here, given we have the equation in factored form, how do we do that? Well, to do that, we can have your equation written nicer in factored form, because I was looking at this factor, it was hard for me to think about a zero here because it was a monomial. So I rewrite my expression like this, where the first term here, well, my first factor here, I want to see it in a binomial format, right? Instead of negative 15x, well, basically, if the x has nothing added or subtracted from it, but it's there, that would be a zero, because this part would be 0 if x equals 0. That makes that makes 0 a 0 of h of x, because when you replace x by 0, h of x will be 0. So this factor here will cause 0 to be a 0 of the polynomial. For this one, when you set this factor equals 0, x will be negative 5. Also, negative 5 will be a 0 of your polynomial, because when you plug in negative 5, 0, it will give you a 0, and this one too. So that's why I put it in separate form, and then I set this part equals 0, which will give me x equals 0, and then so on. I found all the zeros of this polynomial, which are x equals 0, x equals negative 5, and x equals 11. Versus if I had the graph, you remember you located the connection where the graph crosses the x-axis. But over here, you need to solve each part or each factor equals 0, and then you would find the zeros. So that's how you get the zeros. Next, you need the multiplicities, because that's what they're asking you here. They ask you for the intercepts, which means where f of x equals 0, and also how would a graph crosses the x-axis, how would a graph cross the x-axis at this 0? So we need to look at the multiplicity. Well, the multiplicities are the exponents of the factors. Well, we have a multiplicity 4 here, 5, and 3. And so that means we have an even multiplicity and two odd multiplicity. Now let's answer the questions. Question number 1. They say let's complete this blank. The multiplicity of the least root. Which one is the least root? root here of the three we found, or 0. X equals 0, X equals -5, X equals 11. So that the least root is -5. What was the multiplicity for -5? That is 5. The multiplicity of the greatest root X equals 11 is, what was the multiplicity for 11? That is 3. And the other one, the only one that's left, is 0. And the multiplicity was 4. Okay. Now, since we know the multiplicities, we know that whether they are even or odd. Now we can tell what would be the effect on the graph based on whether the zeros are the multiplicity of the zeros is even or odd. So the least zero was -5. With a multiplicity 5, we expect this to cross the x-axis. With the greatest one, with x equals 11, it's also even, it's also odd, then we expect the graph to cross the x-axis. With the other one, which is 0, the multiplicity 4 was even, we expect to touch and bounce. So that is B. And basically, we know as a summary of all we've done here, the graph of a function crosses the x-axis at the 0 of multiplicity odd. When the multiplicity is odd, the graph crosses and touches the x-axis and turns around at the 0 if the multiplicity of the 0 is even. So that's what we look for when we're looking for the multiplicity. If it's even, we cross and we touch and bounce and turns around. If it's odd, it crosses the x-axis. And then the conversation about how it crosses, if it's lower, then the multiplicity is higher. If it turns slowly, then the multiplicity is higher. The higher is the multiplicity, the slower the movement on the x-axis will be. So in this next example here, we are given the problem, the polynomial function in general form. Well, remember, we go from given the graph of the function to analyze. We were given a function that was given in factored form, where we could see clearly what were the zeros by setting up each factor equals 0 and solve to find the zeros, and the powers were the multiplicity for each 0 we get from the given factor. But in this case, we are given a polynomial function in general form. Well, when it's given in general form, we must factor to answer those questions about the multiplicity or the zeros. So we will factor. Well, up to this point, the only tool that we have to factor those expressions is factor by grouping, because we haven't learned so far other methods to factor a higher degree polynomial. So that's why we will attempt to see if by grouping would work here. So that's going to be my first group. Well, even if you have other methods, if you are not asked to use a specific method, I think factor by grouping is a nice way to go quicker, and it's a pretty powerful tool to factor expressions if it's possible to do so. So I would always try to see if factor by grouping would work. Now we have the two groups. That's my first group, and that's my second group. Now we're looking for the GCF of the first group. But first, I can check to see if there can be a common factor outside all the way. So let me see if 3 cannot be the common factor. Yes, 3 can be. So I'm going to factor the GCF, which is 3 here, out. So that's x cubed minus 8 x squared minus 4 x plus 32. So that's this. And then now I keep my groups the same. And for the first group, the GCF would be x squared. So that is 3 on the outside. And then GCF of this group is x squared. So divide each term by x squared. I'm going to have x minus 8. And the GCF of my second group, feel like I can factor negative 4 out. So that's x minus 8. And then finally, I can refactor this as 3 factor x squared minus 4 factor x plus minus 8. But I'm not done yet. This can be factored again by using the difference of two squares. So I can completely factor this as 3. So that's x squared minus 4 is the same as x squared minus 2 squared. The difference of squares is if we have a squared minus b squared, that is a plus b times a minus b. So my a is x and b is 2. So that's x plus 2, x minus 2 times x minus 8. So having this is the factored form of my polynomial h of x. That's the factored form. I can find the zeros just like we did earlier. I can set this part equals 0, x plus 2 equals 0. I get 1, 0, that's x equals negative 2 by subtracting 2 on both sides. I can take the other one. This one equals 0, so that's x minus 2 equals 0. So x equals 2. And then the last one, I can do the same thing. Can take that part equals 0, that factor equals 0. So x minus 8 equals 0, adding 8 on both sides, x equals 8. We have all the zeros. We can tell which one is the greatest, which one is the lowest, and then the other one. So now we can tell, like when I'm looking, I can tell that the power for each is 1. So multiplicity is 1 for each. And obviously the degree was 3. So clearly the multiplicity, when you add them, it would give you the degree of the polynomial. Now let's answer the questions. Multiplicity of the least root. The least root was -2. -2 is 1. The multiplicity of the greatest root was 8. Multiplicity was 1 for all of them, obviously. And then the other one, +2, multiplicity is 1. Now, for all of the multiplicity, since they are the same, we expect the same impact on the graph based on whether we have an even or odd multiplicity. So we have an odd multiplicity 1. So all of the at all of these locations, -2, 8, and 2 on the x-axis, we expect the graph to cross the x-axis. So at x equals -2, which is the least, we expect to cross the x-axis. We expect the graph to cross the x-axis. At the greatest one, x equals 8, we also expect the graph to cross the x-axis. C. And at the other one, which is +2, we also expect the graph to cross the x-axis. Okay, for this example, we will be talking on the end behavior of a polynomial function. So I have this table that summarizes the different outcomes when it comes to the end behavior of a polynomial function. Well, the two things that we're going to focus on in order to describe how the polynomial function behaves is the sign of the leading term, the sign of the leading coefficient, and the degree, whether it's even or odd, and whether the leading coefficient is positive or negative. So if you have a polynomial function with a leading coefficient that is positive and the degree is even, so you expect to see both sides of the polynomial function look up. It would end on the positive side of the x coordinate, so above the x coordinate, both ends of it. So that's why you have, if its coefficient, leading coefficient is positive and degree is even, both sides rise. It rises on the left and rises on the right. Now let's see if you have a positive leading coefficient and then you have an odd degree. If you have positive coefficient and odd degree, you will have your polynomial function that rises, that falls on the left. It falls on the left and rises on the right. That's if you have a positive and then odd degree. Positive leading coefficient and odd degree. If you have a polynomial function where you have a negative coefficient with an even degree, then you're going to have your polynomial function that falls on the left and falls on the right. That means both sides look down, negative and even, negative coefficient and even degree. And finally, if you have a polynomial function that has a negative coefficient, leading coefficient, and an odd degree, you expect to see that polynomial function that rises on the left side goes up, and then the right side would go down, which is the opposite of having a positive and odd, a positive coefficient, leading coefficient, and then odd degree. Now, with this information, we can go to this example again to first identify the leading coefficient, see whether the degree is even or odd. The degree here, 3, is odd. And then the coefficient, positive 3, so that's positive. We have a positive coefficient and an odd degree. Let's go back to the table to see what we have as a result. Positive and odd, you expect the polynomial function to fall on the left and rise on the right. Positive coefficient and odd degree. So falls on the left and rise on the right. So that's D. Falls on the left and rises on the right. And then now they are asking me to determine the roots of H, enter the solution. So the roots are what we got from the previous problem. Remember, it's the same problem we solved earlier. This one. So the roots are gonna be -2, 0, and 8. Well, if it was a different problem, we would do the same process here to solve it. But since it's the same problem, we can just grab the solutions from here, -2, 2, and 8. So the zeros are the roots of this, determine the roots of H. So that's -2, 2, and 8. And they say multiplicity. So that's the least one is -2, multiplicity was 1. The greatest one was 8, multiplicity also 1. The other one, 2, multiplicity is also 1. Now, at the least root, -2, the graph, what happens? You have multiplicity 1, it crosses the x-axis. At the greatest root, 8, it's a multiplicity 1, so also crosses the x-axis. And at the other multiplicity, at the other root, positive 2, multiplicity was 1, we expect it also to cross the x-axis. Now, they ask me to determine the y-intercept of H and give it in the form xy. So we need to give it in ordered pair. So h of x is this. So let me write it again here for you. It's h of x equals 3x squared minus 24x minus 12x plus 96. See again, 12x plus 96. Now, they want me to tell whether this is to find the y-intercept for this. Well, y-intercept, the y-intercept is when x equals 0. So that means you can plug in, you can find h of x, h of 0. So we can say that that's 0, h of 0 would be the y-intercept in x, y format. So y-intercept is 0, h of 0. So h of 0 would be 3 times 0 to the third. Well, that's to the third. And then minus 24, 0 to the second, minus 12 times 0 plus 96. Everything that's 0 here, we will reduce to 0. So h of 0 is 96. So your y-intercept is x equals 0, y equals 96. Now, this function, they ask me whether it is even or odd. Now, the question we need to answer here, the question we need to answer here is, now how do we know whether a function is odd or even? So we have an algebra way to prove that, or we can look at the function and identify whether it is or not by the expression of the polynomial function. But we remember odd functions are when f of negative x is negative f of x is the same as negative f of x. So that means when you replace negative x in the function, it just factors the negative sign out, and the same function will be just multiplied by -1. So multiplying negative x by -1, it's like multiplying the actual function by -x. That's when the function is odd. The function will be even is when multiplying negative x by -1 does not affect f of x. So that means f of negative x is the same as f of x. So the y value of negative x is the same as the y value for positive x. Negative x and positive x, they have the same output. That's when you would say the function is even. But also in the case of a polynomial function, you can say that if the polynomial function is, if the polynomial function is even, if the polynomial function is even, if all of its terms they have even exponent. So if all the terms of this polynomial function have even exponent, this polynomial function is even. Or if the terms, it is odd if the terms have all odd exponents. And if you have mixed exponents, odd and even, then you have a polynomial that is neither odd nor even. Well, let's go. Let's see what we have here. We have exponent even, odd and exponent even. So then this polynomial would be neither odd nor even. And we can use the information we've built from the questions earlier to graph the function. But since the graph is given to us, we can just identify to see which one would work. Well, the first thing we can use is to find the graph is to use the x-intercepts. The x-intercepts. So what are the x-intercepts? The x-intercepts were -2, 8, and 2. -2, 2, and 8. Well, it can't be that. This one is not. This one is not, because this is -8. -2, 2, and 8. -2, 2, and 8. It's either one of these two. It's either C or D. Now, how do we know which one? Well, we can look at the end behavior. What was the end behavior? The end behavior earlier, we decided based on the fact that we had odd degree and positive coefficient, the graph of f of h of x will fall on the left and then rise on the right. Let's see which one of them give us this conditions. It falls on the left, so that's this one, and falls on the left and rises on the right, so that's going to be D. So D is the correct graph for h of x. All right, in this next example, we are trying to continue the study of the end behavior of a function using the leading coefficient. But the difference in this problem is that it's in factored form. Now, how do we find the leading term of the polynomial function when the function is given in factored form? So the leading term will be given as you take each factor you multiply them, but you don't need to take the constant though. You can just take the x term raised with the power or the multiplicity with the multiplicity. So that's x here with the multiplicity 3 times x with the multiplicity 1. So when you multiply all of these, that will give you x to the power 6. And if the x factors, they have coefficient, you need to raise them with the coefficient, and because that's when you're going to multiply and get your leading coefficient. For example, if you have f of x equals something like, say, 2x squared times 3x minus 5 to the power 2 times x, 2x plus 1 power 3, then you're going to need to take the first factor, 2x squared times 3x to the power 2 times, that's plus 1, times 2x power 3, and then perform this multiplication. Perform this multiplication. My picture was in the way of the things that I was writing. And then that will be your leading term for this function. So you may find yourself in a situation where you need to find the leading term using this technique. When you have the expression or the function given in factored form. So that would be what you call the leading term. But in this case, it's the coefficient is 1. So for all the x values, so that's why it's automatically x to the 6th power. So the leading term is x exponent 6. Coefficient is 1, which is positive. And then the exponent, the highest exponent, the degree is even. Let's look again to see what happens here on the table. Positive and even, positive even, it rises on both sides. Positive and even. So you have the graph that rises on the left and rises on the right, which makes the answer G. And now the next thing they ask is to find the zeros and their multiplicity. Well, S of x is x squared, that I can write as x minus 0 squared, times x plus 6 to the third, and then x minus 4. So when we set this equals 0, x will be automatically 0. This one, x equals -6, or x plus 6 equals 0, x equals -6. And then you get x equals equals 4. So the zeros are -6, 4, and 0. Now we can answer those questions. They say the multiplicity of the least root, which is 6, is, what was it? Well, it was 3. The multiplicity of the greatest root, which was 4, was 1. And the multiplicity of the other one, which is 0, was 2. And we know when the multiplicity is even, you have multiplicity is even, you have a touch and turn with the x-axis on the x-axis. When the multiplicity is odd, you have a cross on the x-axis at the location of that 0. So at the least, that's -6. At the least root, you have -6 here, and then you have a cross because it's odd. So that's C. And at the greatest root 4, we have also a cross because it's odd, 1. And at the other root, which is 0, you have a touch and turn because the multiplicity is even. And they ask me here to find the y-intercept. The y-intercept is when x equals 0. So that would be 0 comma s of 0. Now let's find s of 0. S of 0 is 0 because that's going to be 0 squared times x plus 0. I mean, we know x is 0. That's 0 plus 6. 0 plus 6 squared to the third, plus, not plus, times x minus 0 minus 4. Because you have this 0 multiplying everything, so it's automatically 0. So your y-intercept is 0, 0. And the next thing we want to see is whether the function is even or odd. Well, clearly we have different type of exponents, because when you have a function that is in factored form here, if you would have had the same exponent, you cannot, there's no way you can have the same exponent when you have various exponent here for each factor like this. Even if you had the same exponent, you would still have terms with exponent not even in terms with exponent not odd, or so you would not have a uniform exponent for each term. So that said, you will fall in the situation where your function is neither odd nor even. Now, this we have the graphs here. We're going to identify which one is the can be, or that which graph is closer to be the correct graph of that function that was given to us. First, we need to identify the zeros. Zeros was 4. Let me see again. They were 4, 6, -6, and 0. So x equals -4 here. So this one is not included in our choices. This one is not because 4, it's not -4. And we got 4, 0, and -6 that we can consider it to for deeper look. 6, -6, 0, and 4. These two, C or D, will be our answer. Now we're going to use the end behavior to determine which one of C or D that could be the answer. And the difference is what? We see that both sides look up in one and both sides look down. That means we have this one is coefficient is positive and even degree. And this one says coefficient is negative and then even degree. That's why you see both sides fall. It falls on the left and falls on the right. And then on for C, it falls on the left and falls on the right. And then for D, it says rises on the left and rises on the right. And I believe that's what we had as the end behavior for the function, rises on both sides. So that makes D the correct answer. So D is the correct answer. So in this next example, they describe the polynomial functions for you, the polynomial function for you, and then they're gonna want you to give the equation of the function and then eventually answer some other questions. So here is it. They say a polynomial function of degree 4 has the following characteristics. The first thing is the leading coefficient is 1. They say a 0 of multiplicity 1 is x equals 6. X equals 6 is x equals 6 is a 0 of multiplicity 1. So that means you're gonna have a factor that is x minus 6. And then you have another 0 that has a multiplicity -1. So x equals -1. So you have a factor that is, you're gonna have a factor x plus 6, x plus 1, x plus 1. And then there is another 0 of multiplicity 2, x equals 9. So you're going to have a factor x minus 9, multiplicity 2, so it's squared, which will give you, since the leading coefficient is 1, you're going to have p of x that is x minus 6 times x plus 1 times x minus 9 to the power 2. So that's p of x. Let me put it here. P of x equals x. It doesn't matter which order you put your x, your factors, minus 6, x plus 1, x minus 9 squared. And that gives me the polynomial of degree, the equation of the polynomial of degree 4 described in the characteristics above. Now let's see what they want me to find. Oh, that's it. That's it for this part. This is for this example. Next, they want me to look at this graph, and then to determine, first they want me to identify that this graph is complete. And here are the reasons why I can conclude that this graph is complete, because I can see all the roots of this graph and all its end behavior, including the y-intercept of this. So that means we can see the most essential part of this graph. So that's when you know it's complete. You see the end behavior, you see the all the roots, you see the y-intercept, then yes, this graph is a complete graph. Well, we know that it would continue to extend, but there is nothing in terms of characteristics that we are missing from this graph. So that's why we say it is a complete graph. Now, use this graph to answer the following questions. Note, all x and y intercepts are integers. So we need to, so we have y-intercept, x-intercept here. Now let's see what are the questions. So the reason we talked about complete graph is because some of the questions you can only answer them when you have a complete graph. Even if you're typing you're using your graphing calculator to graph, some of the questions you don't rush to answer them if you're not sure that your graph is complete. You have the right setup of your viewing in order to see the graph completely, including the end behavior, the zeros, and the y-intercept, to make sure that you can make the conclusion. Now, first, you have to list the roots with the even multiplicity. Even multiplicity, we need to remember the graph touch and turns. Well, for all the time that I see on this graph that the graph touches the x-axis, it touches and turns. So that's -3 and -1 are the two zeros, and for both of them, the graph touches and turns. Okay. Well, we have no other zeros, so that means there are no zeros for which the graph crosses. So no zeros for odd multiplicities. The graph crosses. Now they ask me to determine the y-intercept. And we need to report the y-intercept as an x and the y coordinate. We need to remember that the y-intercept is where the graph touches the y-axis. But as a ordered pair, we can tell that is x equals 0 and y equals 9. X equals 0 and y equals 9. And then now it says determine the factored form of f of x. The factored form of f of x, since we have a polynomial function, they did not tell me. Let me see if they tell me what was the degree of the polynomial. Well, they didn't tell me, but I assume that these are both even and equals 2. So that's going to be a factored form of this will be f of x equals a x plus 3. If I need to get minus 3, I need to have a factor x plus 3. Because when I set it equals 0, I would get the negative 3 squared, because it turns and it's even degree. Well, I assume that it's 2 because the turns is pretty quick, right? So that's how I say it's 2. If it was slower, flatter, then I would be more concerned about saying that it's 2, but it's not flat. It's quick, so that's why I say the multiplicity is 2. And the other one would be the same scenario, so that's x plus 1 with a degree 2, with a degree 2. So x plus 1, because that's when I put this x plus 1 equals 0, that's when I would get x equals negative 1. Just explaining this to make sure you understand why it's x plus 1, not x minus 1, as it is in the zeros or roots. Now, we're not done yet because we have an a here needed to be found. So we're going to just try to use the y-intercept so we can find this the zero, the value of a. So the y-intercept means y equals 0, y equals 9, y equals 9 when x equals 0. So that's 9 equals a times 0 plus 3 squared times 0 plus 1 squared, right? So that's 9 equals a times 0 plus 3 is 3, 3 squared is 9 times 1. So if that's a 9 equals 9a, divide by 9, we get a equals 1. So we get f of x. Oh, I didn't even see they said that the degree is 4. So my reasoning was good, but yeah, you may want to they may have to say it for you to identify what your power will be. So a equals 1, so f of x equals x plus 3 squared times x plus 1 squared. So that is the polynomial function that was given on this graph. This next example is the same as the last one we did. So the graph of the function f below is complete for the same reason we talked earlier. So we can go quicker now. First question, they want me to determine the roots for which we have an even multiplicity. So let me identify all the roots first. So x equals 1 and x equals 6. Well, that's a touch. At x equals 1, we have a touch and turn. So that's an even multiplicity, x equals 1. At x equals 1, the graph touches and turns. That's why we say that the multiplicity of the 0 x equals 1 is even. Whereas at x equals 6, the multiplicity is odd, because at x equals 6, the graph uh, crosses the x-axis. So that's why we say that at x equals 6, we have a multiplicity that is odd. They say determine the y-intercept and give it in xy format. Well, y-intercept is where the graph touches the y-axis. So that's 0, x equals 0, and y equals 2. And then now we can give the function. Remember, we have 2 zeros, right? We have 2 zeros, x equals 1 and x equals 2. I mean, what x equals 6. but the hint is that the degree of the polynomial function is 3. And obviously, we knew that it would have been 3 because we have one even, one odd, and then the turn here is fast, and this one is also fast. So we know that it's going to be 2 multiplicity here and then 1 multiplicity here, which would mean that the function f of x will be x minus, is it minus x plus 1, the multiplicities, that not the values. Multiplicity for this 0, x equals 1 is 2, and multiplicity for the 0, x equals 6 is 1. Multiplicity for x equals 6 is 1. So then we're going to have for the 0, x equals 1, that's x minus 1 to the power 2 times x minus 6 to the power 1, which would be, and then we're not forgetting because we don't know what the coefficient is. So we put an A and use the y-intercept to find the value for A. So the y-intercept is 0, 2. That's y f of x equals 2. And then x equals 0 minus 1 squared and 0 minus 6. So that is 2 equals, that's negative 6a, right? That's 1, and that's negative 6. And negatives, you will multiply them all. So a times 1, a times negative 6, negative 6a. And then if we divide by negative 6, we would get a equals negative 1/3. We simplify by 2. So the polynomial function that was described on the graph here was negative 1/3 of x minus 1 squared times x minus 6. So that is the polynomial function that we should have found in this problem. We can even write it up here, negative 1/3 x minus 1 squared times x minus 6.